is go through the test. And so feel free to ask questions as I'm going. I'll try to bring up the points that seemed important as I was grading these. The first one, so exam 1. The first question was a unit conversion kind of thing. And we were converting negative 80 miles per hour squared to millimeters per minute squared. And give your answer in scientific notation. Okay, so start with negative 80 miles per, I'm going to think of this as hours times hours. Since we have 2 hours in the denominator, we have to do the conversion of each of those. So 1 hour is 60 minutes. And you have to do that twice to cancel both of those 2 hours that we started with. And then 1 mile is 1609 meters. Okay, so now if you did all the cancellations, you're in units of meters per minute squared, okay? But we still have to go from meters to millimeters. So to do that, you have to, so we're trying to go from meters to millimeters. And the way to do that is to think, so start with 1 millimeter, start with the thing that has the prefix on it, and then think, what's the definition of that prefix? Milli means times 10 to the minus third, okay? So 1 millimeter is equal to 1 times 10 to the minus third meters. So there's your conversion, okay? We want to cancel the meters that are on the top right now. So I'm going to put the 1 times 10 to the minus third meters down there. The 1 millimeters up here. Those cancel, and now we're in the units we want. And if you punch this into your calculator, you get negative 3.576 times 10 to the fourth millimeters per minute squared. A lot of people did everything right except, I mean, I'd say at least 5 people did everything right, but then did this conversion backwards to go from meters to millimeters. Yeah, I mean, I know it's easy to do. So remember that when you're doing that conversion from something with a prefix to something without, write down the thing with the prefix, one of those, you know, and then make the replacement of like milli means this. And if you do that, you'll get it right. You can also just sort of sanity check yourself by saying like, okay, how many millimeters are there in a meter? Are there a lot or less than 1, you know? A millimeter is really little. So you can't have 1 meter be less than 1 millimeter, you know what I mean? So those are kind of the 2 ways I would say to think about that. Anybody have any questions about that? All right, the second one was the ball rolling on the ramp. So the ramp looks like this. You can draw this at an angle or draw it horizontal, it doesn't matter. Actually, on my paper, doing the solutions, I wrote it horizontal, but here I'm doing it at an angle. So there's the point B, the point A, and the point C. And this thing, it starts at A, takes 2 seconds to get to B, then comes back down, gets back to A in 2 more seconds, and then takes half a second to get to C. So this is 2 seconds, this is 2 more seconds, this is half a second. Does it make sense that, well, I didn't give you the distances, but let's see. A to C is 1 meter, and it's 3 meters from A to B. Does it make sense that it would take so long to go from A to B and B back to A, and then such a short time to get from A to C? It does, because as this is rolling, it's speeding up. So the fastest it's going to be going is from A to C. Okay? That doesn't matter for doing this problem, but just for making sort of sense out of it. Okay, so this is what the thing does, and now we're going to label it based on our choices. So the first choice is 0 time is at the start of the motion. That means that at this instant, the stopwatch says 0. At this instant, it says 2 seconds. The times just keep adding up. So at this instant, it says 4 seconds, and here it says 4.5 seconds. So the times, you just keep adding them. The positions, you don't keep adding them. So for the positions, we're going to label each of these points, and then whenever it's at that point, that's the position that it's at. So our 0 is, let's see, 0 is at C. And our positive direction is down the ramp. So that means anytime it's going this way, it's in the negative direction. Okay, and now we'll label these. Well, remember that position is, you can think of it as 2 things. The magnitude of the position is how far the thing is from 0, and then the sign tells you which side of 0 it's on. Well, how far is A from C? Oh yeah, you're not doing this today? Okay, I'll just keep talking. So it's 1 meter from C, right?
Yes.
Thank you. And then it's in the negative direction. So this would be -1. And then how far is B from 0? 4, yep. And it's also in the negative direction from 0. And so now we can just follow this path along the whole way. And I always make a little table with times and positions. At time 0, the position is -1 meter. At time 2 seconds, the position is -4 meters. At 4 seconds, the position is -1 meters again. And then at 4.5 seconds, the position is 0. Okay? And then it's just a matter of plotting these out, pair by pair. 0, 1 is the first point, 2, -4, 4, -1, 4.50. So if the positions are -1, -2, -3, -4, and the times are 1, 2, 3, 4, 4.5. So it's going to start at 0, -1, then 2, -4, 1, 2, -4, then 4, -1, and then 4.50. Really, in reality, so this is how I've always done graphs like this, and that's fine for this kind of question. But in reality, it's actually impossible for an object to change its velocity instantly. Okay? There's no way it can do that. Which means that it can't, maybe at time equals 0 it was already moving this direction, so we can't really say anything about this first one. But we know that it can't be moving in the negative direction, stop, and get to 2 seconds, and then instantly be moving in the positive direction. So really this graph has to look something more like this. Okay, just for understanding how these work. And then you could look at this graph and think like, okay, where is the acceleration, positive, negative, the kind of stuff that we've done in labs. Okay, and then the third question. An object is launched straight up into the air at 20 meters per second, and the starting height is 2 meters. So it goes straight up, reaches its highest point, and then starts coming back down. And we want to calculate the height of the object at its highest point. And we want to calculate its velocity just before it hits the ground. Okay, so the first thing we have to do is make our choice of our time equals 0, our time final, and our 0 position and our positive direction. Time equals 0 for part A to figure out the highest point is the instant that it's launched. Time final is the instant that it reaches its highest point. So the fact that one of our instants happens when it's at its highest point tells us there's one bit of information that we're going to use eventually. Do you remember what that is? What do we always use anytime a problem asks us about the highest point?
Oh, the velocity is 0.
That's right, velocity is 0. And in 2D, it would be the y component of velocity is 0. Our 0 position, I'm going to choose at the ground, and I'm going to choose the positive direction up. We don't know how long it takes, so we don't know time final. We know the acceleration is negative 9.81. We know the initial position is 2 meters. We're trying to find the final position. The initial velocity is 20 meters per second. That's given to us in the problem as a speed and then a direction. It's launched up. And up is positive the way I chose it, so that's why this is positive 20. And then finally, the one that we knew we were going to use eventually, v final is equal to 0. Okay, so to find PF, the equation we can use is 2a times the quantity PF minus PI is equal to VF squared minus VI squared. So negative 19.62 times PF minus 2 is equal to 0 squared minus 20 squared. And there were a handful of people who got to this step and then just had algebra problems. I didn't take off much for that. I took off 1 point if your only mistakes were algebra or whatever. But I want you to notice a couple things about this. First of all, that negative is not included in this square. Okay, so after you square this 20, you still have that negative there. I saw that a couple times. Okay, and then the second thing is this negative 19.62 is multiplied. You have to distribute that if you're going to multiply this. So I had people write it like this and then write negative 19.62 times PF minus 2. But that's not how it works. You also have to multiply that negative 19.62 to the negative 2. Okay. And if you calculate this, you get PF is equal to 22.39. So that's for part A. And then for part B, this is kind of a more serious, I mean, like not serious, but like it's a real physics concept. So for part 2, it says we're trying to calculate the velocity right before it hits the ground. Well, the instant that it hits the ground is not either one of these times that we chose for part A. So you have to re-choose either your time equals 0 or your time final on this. Well, in this case, it has to be time final. Sometimes you get a choice of which one you want to make it. So I'll keep my time equals 0 the same. But my time final now is going to be the instant right before it hits the ground. And since we chose a different time final, what that means is we can't use any of the time final related information that we used in part A. Okay? And if you use those, it'll mess up the problem. And so, like, for example, a lot of people used either velocity final is equal to 0 for part B, or they used that the position is 22.39 for part B. You can't do either of those because we have a new instant that we're doing our calculations for. What you could do, I don't think it's worth the effort, but you could make your time equal 0 where the thing was at the highest point, what it was at the highest point, and then work from there. But it doesn't, I don't know. It sort of makes you think unnecessarily about it. So let's list out what we know and want. We don't know how long it takes to hit the ground. We know the acceleration. We know the initial position is 2. This time we know the final position since it's on the ground, and that's where my 0 position was. This is 0. Initial velocity is positive 20. Final velocity is what we're trying to calculate. And you can use the same equation again, 2a times the quantity, PF minus PI, is equal to VF squared minus VI squared. So we have negative 19.62 times the quantity, 0 minus 2, is equal to VF squared minus 20 squared. And so negative 19.62 times negative 2 is positive 39.24. And that's equal to VF squared minus 400. Add 400 to both sides, and you get VF squared is equal to 439.24. Take the square root of both sides. And this was the last place where you could make a mistake. remember that you're taking the square root of a variable, and so you have to consider the possibility that the answer is positive or negative. So this should be plus or minus 20.96. But now you have to think, which one is it? Which way is this object moving? We're talking about on the way down when it gets to the ground. That's negative, the way I have it set up. And so we want the negative there. Any questions about that one? Okay, and then the last one. We had a vector that had a magnitude of 15 and makes an angle of 20 degrees with the horizontal. And we want to calculate its components in two coordinate systems. The one we're used to, and then second, one where the x-axis is up and the y-axis is to the left. And in either case, you draw the coordinate system. And then without rotating the vector at all, you put the tail of the vector at the origin. So that would go like here. And now you want to figure out the counterclockwise angle from the positive x-axis to the vector. For this one, it would be 180 if we made it all the way to the negative axis. We're 20 degrees short of that, so our theta is equal to 160. And so the components are 15 times the cosine of 160, 15 times the sine of 160. And you get negative 14.10, 5.13. And remember, you can always sort of sanity check your answers by thinking what the coordinates would be where the head is. This is in the second quadrant. So we're going to have a negative x value and a positive y value. And that's what we got. So that's part A. And then for part B, just do the same thing again. So there's the coordinate system. Here's the vector. And this angle is 20 degrees. So now what's the angle from the positive x-axis to the vector? It would be 90 if you went all the way from x to y, but we're 20 degrees short of that. And so this is 70 degrees. And so the components are 15 times the cosine of 70, 15 times the sine of 70, and you get 5.13 for the x component, 14.10 for the y component. And again, you can sanity check that because in this coordinate system, what quadrant is the head in? It's between the positive x and y, so it's in the first quadrant. So those both have to be positive. Okay, any questions about that? All right, well, please, look your test over, and if you want to talk about, I'd be happy to talk about if you have grading questions, or I'd be happy to talk if you feel like there's some stuff that you're not understanding as well as you'd like to. But this is a good chance to kind of assess where you are right now. So yeah, please, let's just talk about that and make sure that things are going the way you want them to go. as far as points, remember that your final score can replace one of your first 4 exams. So the points themselves aren't a problem at all. I mean, your exam 4 can just totally erase this score. So the thing to think about instead is not like whether that score hurts you or not. It's just whether your understanding of this material is where you feel like it should be. Okay? All right. Any last minute questions? So please come talk to me if you have any questions about this. Okay, so last time, so we're starting to talk about Newton's second law and 2D kinetics. And we figured out just by reasoning out what we know about Newton's second law and what we know about the acceleration in free fall, we were able to figure out what the force of gravity is on objects. So that's a big deal. So we know how to represent the force that gravity applies to things. And then we fiddled around a little and figured out, based on what we know about the force of gravity, what the force is that, like, the scale applies to somebody standing on it, and then we did it in an elevator and some stuff like that. Now what we're going to do is sort of a more careful, like, step-by-step approach for using Newton's second law to calculate forces and accelerations. And before I get into that stuff, we have to talk about free body diagrams. So, okay, free body diagrams. One of the first years I taught this class, somebody came up and asked me about the free base diagrams, and I was like, please don't tell people I'm teaching you about free base diagrams.
What's the difference between free base and free body?
Free base is like smoking cocaine. So I really don't want to be associated with that. Okay, so draw a free body diagram. I want you to draw a free body diagram every time you use Newton's second law. And I'm going to abbreviate free body diagram FBD. So every time you use Newton's second law, there has to be a free body diagram. And here are the steps for drawing a free body diagram. And I'm going to illustrate it as I go with this, this guy that I only seem to draw during the free body diagram portion of this class, but I like drawing him for some reason. I like his tank top. I like his attitude. So the first step is draw a closed outline of the object you're analyzing.
What do you mean closed out?
Okay, I'll show you some things that don't qualify, but basically what we're trying to do with a free body diagram is be very clear about the boundary between, we want to define a boundary where inside the boundary is our object and outside the boundary is everything else. And so we don't care about the eyes or the, what's in his pockets or anything. We only care about defining that boundary. So draw a closed outline of the boundary with no internal details. And no outside objects. So like, for example, if the object that you're analyzing is this man, something like this is the outline, okay? What you don't want to do is, so here's one thing you don't want to do, because it doesn't clearly show the outline. You don't want to do this because there's internal details in that. The only thing that's relevant to us about our chosen object is the boundary that separates it from the surroundings. And then the last one is don't do this, because putting that ground in there creates ambiguity about what we're considering in our analysis. Like, are we considering the top layer of grass? How deep of the grass are we, you know what I mean? And so all you want is that boundary. Okay? The second step is draw a downward arrow from the middle of the object and label it with either the object's weight, if you know what that is at the start, or you can also label it with mg just to show that that's the weight. So label it with the object's weight. Or you can just label it mass times g. Remember that the meaning of g here is positive 9.81 meters per second squared. So,
Wait, why positive?
yeah, that's a good question, and I think everybody thinks about that from, at some time. So the magnitude of the acceleration of gravity is 9.81 meters per second squared. The direction is down, okay? For us, we tend to put our positive direction up, which means that that gravity acts in the negative direction. But there's no reason that has to be the case. So we sort of want to separate the magnitude of that force from the direction. The direction we deal with separately. So this is what this should look like when you put the weight in.
Can we not just draw it as like a circle or something to look actual?
Yeah, you can. But I do want you to get in the habit of drawing an outline of an object. And I know the people who've taken physics before, a lot of times when you first take physics, people do their free body diagrams just as like a dot with, forces going in different directions. I don't want you to do that, because at the end of this class, we're going to start doing calculations, treating things as rigid bodies that do have lengths and stuff. And once we do that, where those forces act is important.
Okay, so we'll start with like particle.
Yeah, right. Eventually we will. And so this is kind of a setup for that in a way. Okay, so as far as the sign of the weight, notice that, so the magnitude is mg. The direction, which is where that negative would come from if it's going to be negative, is shown by the direction of the arrow. Okay? And then the last step, the third step, is at each place where the object's boundary makes contact with the surroundings, draw an arrow in the direction of the contact force. And label that arrow with a variable, or if you know the value, you can put the value in. So label it with, let's say, a value or a variable. Okay, so in the case of this guy, he's standing on the ground. We have the weight force down. And last time we figured out that the scale that he was standing on applied a force that was straight up. So I'm going to put this force up, and I don't know, we don't know we're going to pretend we don't know anything about the magnitude, so I'm going to label that with the force R. That's just a variable.
Why aren't you labeling it from the middle?
What?
Why aren't you labeling it from the middle?
The R?
Yeah.
Okay, yeah. Let me finish this thought and then, so R, this is a variable. Okay. All right, well, so there's only two kinds of forces. There's weight, the force applied by gravity, and then there are forces that the surroundings apply to the boundary because of contact. And so wherever those contact forces act, you want to draw that force acting at that point. So yeah, so the ground is pushing up on his feet, so that's where I draw that force. And I think, sort of what you're thinking about this is like, when you're dealing with particles, it doesn't matter where you put it. So you might as well just put them all at the middle. But later, when we get to rigid bodies, it will affect the calculations.
Okay.
Yep. Okay. Any questions about that? Well, the problem we have now is, so great, the weight is easy. You put a downward force, downward arrow, and label it. But I sort of glossed over the fact that we don't know the directions of contact forces for the most part. I mean, this is the only kind of contact force we've thought about at all. So like, say someone's pulling with a rope and it's going over this thing, and like, how do you know what the direction is? So the next thing we have to do is break up all the contact forces into some different categories and talk about in those categories, what's the direction that that force applies, okay? So now we're going to think about contact forces. And okay, so just as a reminder, the force types that we're going to see, there's the weight force. That's the force applied by gravity. And the only other type of forces are contact forces. It would, yeah. We're never going to deal with that, but yes, you would have to treat it that way. It's what it really is a million little balls bouncing off you, so a million little impact contact forces, So, and the contact forces we're going to break up into three categories. So the first one is pushing contact. The second one is pulling contact. And for now, I'm just going to put in parentheses cables, because whenever something's pulling on another object, you can think of that contact being replaced by like a rope or a cable, okay? And then the third one is friction. And friction is only going to happen when objects are sliding, when an object is sliding on another object. Okay, so we already know how to deal with the weight, and now we're moving on to this. So first, let's talk about pushing contact. So what does it mean for two things to be pushing on each other? You can think of it as, so a pushing force is a force that prevents two objects from merging, prevents their boundaries from blending, okay?
So would a car crash be?
That's pushing, yeah.
But if they like combine or like collide, they stuck into each other with that?
Yeah, so there's still like, there's no way for the material to occupy the same space, you know? So even though their spaces are both being diminished, they're still keeping each other out of their space, you know? So a push force prevents outside objects from crossing the chosen object's boundary. So here are some examples of pushing forces. So if you have a rolling cart there, in contact with a rolling cart here, and two forces pushing them together, let's say this is 50 newtons and this is 100 newtons. And let's say this one is 1 kilogram and this one is 2 kilograms. Then where is pushing happening? So for the 1 kilogram cart, there's a pushing force applied by the ground that's keeping the object from sinking into the ground. So there's a pushing contact at the wheels. There's really two of them, but for now we're going to think of it as a single force. And then these two objects, if they weren't pushing on each other, would cross each other's boundaries and become like a single object. So there's also a pushing contact there. And for the 2 kilogram, it's pretty much the same story. There's a pushing contact from the ground that's keeping this thing from sinking into the ground. And there's a pushing contact from the 1 kilogram cart that's keeping the two from blending. Okay? So once you've identified a force as a pushing force, the direction of the pushing force, so the pushing force direction, hold on. Okay, pushing force direction is perpendicular to the surface of contact of contact and toward the chosen body. Okay, so let's think about these again, okay? So in the example above, what would these free body diagrams look like? So a free body diagram of the 1 kilogram cart there's the outline. There's a weight force that's equal to 1 times 9.81. So that's 9.81 newtons down. And we identified these 2 places where the surroundings are pushing on this object. The first one is at the wheels. It's really acting on both of them, but we're just going to put one single force there for now, okay? But okay, so let's think about this rule and figure out what the direction is. The surface of contact for that pushing force from the ground is the ground, you know, so the surface is horizontal. So perpendicular to that is either up or down. And then finally, then you have to identify, like, what do we want, up or down? A vector only has a single direction. We want toward the chosen body, so we want that one. And I'm going to label this capital N for now. I'll tell you why later. And now the other place where there's a pushing contact is over on the right side. Okay? The surface of contact are the sides of the carts. So the surface of contact is like a vertical line. So perpendicular to that is either to the left or the right. We want the one toward the chosen body, so that way. And I'm going to label this R. That's the variable.
Why is it on the right side as it was on the left side of the drawing you made?
Well, I'm doing this one here. So I'm doing the one that's on the left, and the place where it's in contact with the other one is on the right side.
Okay, that makes sense.
Yep.
Question.
Yeah.
Why is there, so there's 15 over the pushing each other left?
Oh, yeah. Thank you. I should have put that in there. I just totally forgot about that. There's a 50 over here. But I do want you to notice that there's no 100 on this one, because the 100 isn't acting on the boundary of the 1 kilogram. So there'll be a 50 on the 1 kilogram, but not 100. And on this one, there'll be 100, but no 50. Okay? So now the free body diagram of the 2 kilogram. So there's the outline. The weight force is 2 times 9.81, so 19.62 newtons. There is a pushing force from the ground. The surface of contact is the ground, so It's perpendicular to that and then toward the body. And then we have to give that a variable name. I'm going to call that N2, just to point out that it's not the same as this one. Okay? Then there's the 100 Newton force over here. And then last, there's a pushing contact on this side from the 1 kilogram. It's perpendicular to the surface toward the chosen body. And this is an important thing with pushing contacts. If you're thinking of the contact between two different bodies like we are here, the magnitude of the force on one of them is the same as the magnitude of the force on the other one. So we'll give this the same variable name. Okay? So these are the same because it's the same contact force, you know? It's the same two bodies that are in contact. Okay, so the two things I want you to notice here are first, a variable is a variable. Mathematically, you could choose any variable name you want for these. You could call it X or Q or whatever, but people tend to use the same ones. So common variable names for pushing contacts. For pushing contact forces are capital N and capital R. N stands for normal. And normal means perpendicular, so it's given this name because it's perpendicular to the surface, like I said. And then the capital R stands for reaction. And the reason you give these the name reaction is because this force depends on the other forces that are applied to the body. Like in this case, how hard are these two carts pushing on each other? Well, it depends how big, in this case, the 50 and 100 are. You know, if you instead applied 500 and 1,000, this reaction force would get a lot bigger, you know. So that's where the name reaction comes from. And then second, for two bodies in contact with each other, let's say two bodies A and B in contact with each other, the magnitude of the force on A is the same as the magnitude of the force on B. So in that case, you want to give those the same variable name. That's what I was saying here. So give those the same variable name. That's a first glimpse at something that we're going to talk about a lot, mostly in labs, Newton's third law, that says, well, like in prose, in words, it says for every action there's an equal and opposite reaction. You've probably heard something like that somewhere or other. So whenever two things are in contact, the force on one has the same magnitude as the force on the other one, and the directions are opposite. Okay, well, let's do a calculation. So let's say that we have a cart rolling along a horizontal surface, and it has a mass of 5 kilograms, and we apply a 30 Newton force to it like that. What's the acceleration vector of the cart? Well, I'm going to start by drawing a free body diagram. So there's the outline. The weight is down from the center. It's 5 times 9.81, so 49.05. And now mentally go around the boundary looking for contact. There's some kind of contact here. It doesn't tell us what, but we just put that in there. And then there's a pushing contact applied to the cart from the ground. Okay? Well, that is perpendicular to the ground toward the chosen body. I'll give it the variable n. And that's a complete free body diagram. So now we can go to Newton's second law. And what are the components of this vector 30 pointing to the right? And assuming we're using just the usual coordinate system like this. That's pointing in the positive x direction, right? So what would be the x component?
30.
30, yep. And what would be the y component?
0.
That's right. And then go to the weight force. We're used to that one, so that's 0, negative 49.05. And then the last force is that normal force. What are the components of that? It's pointing in the positive y direction with a magnitude of n. So it's just going to be 0 for x, positive n. And all those forces are equal to the mass of the body, which is 5 kilograms, times the acceleration. So we have to think now, how is this object able to move? And you have to think like, is it able to move along the x-axis or the right axis, or x-axis or the y-axis? X. And so I'm going to put this in as a variable in the x direction and a 0 in the y direction. Okay? Well, there's two equations here. The x equation says 30 plus 0 is equal to 5a. Okay? So 30 is equal to 5a. Divide both sides by 5 and you get that a is equal to 6 meters per second squared. Well, that's the magnitude of the acceleration, but it's not a vector. But notice that we've already decided what the acceleration of this cart was. We just didn't know what a was, so we couldn't fill in this vector with a. But now that we've calculated this value, we can. Okay? So plug this 6 in here, and you get that the acceleration vector is 6, 0. Or in other words, it's going this direction with a magnitude of 6 meters per second squared. Anybody have any questions about that right now? Okay. Okay, well, let's stop there. And what day is it? Wednesday? So I'll give you some problems like this, free body problems, free body diagram problems. And then on Monday, we'll do pulling.
We keep the tests.
Yeah, keep the tests. Yep.